This is your Physics One-Dimensional Forces review. We're going to start off with free fall. When we draw the free body diagram for an object in free fall, it has one and only one vector on it, and that is the weight. The weight can be calculated using the equation mg. When we use W equals mg, we are just calculating the magnitude of the weight. We just want to know how long that weight vector is. And so it needs to be a positive number. It's just the magnitude. The direction we take into account by that weight vector points down. So we would be subtracting it off if we did sum of the forces equals ma. It's in the down direction. So when we calculate the weight, it's just equal to mg. M is the mass in kilograms, must be in kilograms, and it is a positive number. M is a positive number. You do not have negative mass. G is positive 10 meters per second squared because we don't want to have negative weight. We don't say that an object has a weight of negative 50 newtons. The weight is just 50 newtons, and then that vector points down. Again, M must be in, the mass must be in kilograms, and G has to be in meters per second squared, and that gives us a weight that is a force and therefore in newtons. Our motion diagram for an object in free fall could be one of two options. It could be moving faster and faster down. The acceleration vector would point down. What do you have to do to V0 to turn it into V1? You'd have to pull V0 down to make it longer. Or the object could be, for example, thrown upward, starting with a positive velocity that is getting closer and closer to zero velocity at the turnaround point. The acceleration vector is also pointing down. When you have an object in free fall that is accelerating, then the value of the acceleration is g. That is the only time that a is equal to g, is if the object is in fact in free fall. It is acted on by no other force other than the force of gravity, which gives its weight. In other words, its interaction with the Earth. Next topic are elevators, kind of related to free fall. It's what would happen if your object was not in free fall, but in fact was supported by something. So if we draw the free body diagram for the person that's in the elevator, we have several options. We either could have the normal force equal to the weight, then your net force is zero, acceleration is zero, moving at a constant speed up or constant speed down. We could have the normal force greater than the weight. This is the second option there. If the normal force is greater than the weight, then the net force is pointing up, and the acceleration must then point up. Again, we have a couple options for how that could be. If your acceleration vector points up, it could be moving faster and faster upward, or moving downward but slowing down. Both of those would match with an acceleration vector pointing up. If the normal force is less than the weight, then your net force is down. Weight is greater in magnitude than the normal force. And so therefore the acceleration is down. Once again, net force and acceleration have to point in the same direction, always. So if we have a net force down and acceleration down, that could be because the object is moving down and going faster and faster, the first example, or moving upward but slowing down. So you should be able to draw the free body diagram and motion diagram for any of those options, right? Moving up at a constant speed, down at a constant speed, upward and speeding up, going downward and slowing down, all of those options, and see how the acceleration vector matches the net force, which tells you whether normal force equals weight, it's possible, normal force greater than weight, or normal force less than weight. All of those are possible if you are riding in an elevator. So if you were standing on a scale in that elevator, your reading on the scale may read out what your actual weight is, right? Your weight doesn't change just because you're in an elevator. But what does change is the normal force that is acting on you. So the scale reads out what the normal force is, not necessarily your weight. It only is going to read your weight if you are either stopped or moving up at a constant speed or moving down at a constant speed. Otherwise, it may read greater than your weight or less than your weight. That weight vector on our free body diagrams is, of course, W equals mg, and then if we're on Earth, or near Earth, g is 10 meters per second squared in that calculation. Just because we calculate the weight using 10 meters per second squared does not mean that the object or the person is accelerating at 10 meters per second squared. The only time that A equals G is if that cable breaks. Because if the cable breaks, then what does your free body diagram become? No more normal force, right? Or no more tension on the cable, but just your weight vector pointing down. In other words, the only time that the object would be actually accelerating at 10 meters per second squared, only way A would equal G, is if that cable breaks. And then you just go back to our first example with free fall. Then they would just be in free fall. So we don't actually, if we're riding an elevator, we definitely don't want our acceleration to equal G. However, we could still use that value of G in order to calculate our weight. That doesn't change. Weight doesn't change, normal force does. Next topic is friction. So we have two options for friction, either kinetic friction or static friction. Kinetic friction is the object is sliding across the surface. And that's the value of kinetic friction is equal to mu k times the normal force. Two factors for friction. How rough or smooth the surfaces are, that's mu, the coefficient of friction. And then N is the normal force. With what force are those surfaces being pressed together? Or we have static friction, and that is less than or equal to mu s times the normal force. So static friction could be everywhere from 0, if your object is just sitting on the surface and nobody's pushing on it, to all the way up to whatever the maximum is. There is a maximum static friction, and after, if you push hard enough to reach that maximum static friction, or pull to reach maximum static friction, then the object starts to move. So you can be pushing on an object and have it not move. That just means you're not pushing hard enough to overcome maximum static friction. Remember the shape of the graphs that you generated in Friction Lab. So notice also that kinetic friction force and static friction force, those are forces, so they're going to have units of newtons. Those would be things that could be labeled on a free body diagram. Mu k and mu s, those are the coefficients of friction. Coefficient of kinetic friction, coefficient of static friction. Those are unitless numbers. Again, be careful in problem statements. If you are asked to calculate the coefficient of kinetic friction, you're looking for mu. You are not looking for scripty f. You are a coefficient of friction. You want to focus in on the coefficient part of that, and just treat the of kinetic friction. That's a little prepositional phrase that's telling you which one, right? Don't read coefficient of kinetic friction as you are looking for friction force. That would be those two different quantities, right? Are you looking for the kinetic friction force? That would be lowercase f. Or for the coefficient of kinetic friction, that would be mu. Kind of looks like a fancy U or a M, depending on how you write it, which is a unitless number. If you are told in a problem statement that the coefficient of kinetic friction is 0.30, that is mu that you are being given. That is not F. Because if the coefficient of kinetic friction is 0.3, you were given a number that has no unit, therefore that has to be the unitless number, mu, not the force of friction. So you have to read carefully. If you see coefficient, zero in on coefficient, not on friction. So let's try an example here. We have a 10 kilogram box. It is getting pulled by a rope to the left, and it is getting pulled to the left at a constant speed of 2.5 meters per second. And we are given a little bit more information. We want to know what is the coefficient of friction here, and we would assume that we are near the Earth. But we need to know what that tension is in order to have enough information to solve the problem. So if tension is 37 newtons, what is the coefficient of friction between those two surfaces? So, of course, because we know something about forces, we are going to draw a free body diagram. We know that normal force would be balanced with the weight because it's not accelerating up off of the floor or crashing down through the floor. We know that the forces must be balanced also in the horizontal direction because it's moving at a constant speed. That is the only way that you know that the tension and the kinetic friction force have to be the same length, is because constant speed means acceleration is 0, which means net force is 0 in the horizontal direction, which means that they have to be the same length as each other. not necessarily the same length as normal force and weight, right? We always treat the horizontal and the vertical directions separately from each other. So I have a free body diagram. I knew to draw the free body diagram because this is about forces. So I do sum of the forces equals ma in the x direction and in the y direction. That's just Newton's second law in equation form. So in the horizontal direction, I start with positive forces, add those up, subtract off negative forces. So add up all my forces to the right, subtract off all my forces to the left. So that would tell me that the force of friction, the friction force, minus the tension equals 0. And I know it's 0 because acceleration is 0. That is the only way you know that. You have to analyze what's happening with speed in order to know what's going on with acceleration. Therefore, solving for working towards my variables here, friction force is equal to tension. That's just algebra. And then I don't want to know what the force of friction is. I want to know the coefficient of friction. So I need to get my variable that I'm solving for in this equation. My variable is mu. So instead of writing kinetic friction, I'm going to write mu k times the normal force because Fk equals mu k times the normal force. So I'm just replacing those. And then I'm going to solve that for mu k, and I get tension over normal force. Okay, that's looking pretty good. Do I know the tension? Yes, 37 newtons, looking good. Do I know the normal force? No. In order to find the normal force, now I have to look at my sum of the forces in the y direction. And when I do that, I get normal force minus weight equals 0, add up all my up forces, subtract off all my down forces. Therefore, normal force equals weight. You probably knew that even without writing the more detailed explanation. Normal force would equal weight. So instead of writing W, I'm going to write mg because that's what W equals. Weight is equal to mg. Do I know the mass? Yes, it's 10 kilograms. Do I know g? Yes, it is 10 meters per second squared. 10 times 10 is 100 newtons. So normal force equals 100 newtons. Notice that I use 10 meters per second squared for g. That does not mean that my object is accelerating at 10 meters per second squared. That's just going to tell me about how strong the force of gravity is on this object that gives it its weight. So now that I know that normal force equals 100 newtons, then I can put in my tension, put in my normal force, and I get a number that is entirely reasonable for mu, 0.37, less than 1. I expect it to be less than 1. I expect it to be positive. All of these things are looking good. And it is unitless because I had newtons over newtons means nothing. No unit, 0.37. Do not put a unit on coefficient of friction. Notice that I did not solve for the force of friction here. That's not what I was asked for. I could have, but that wasn't what I was asked for. I was just asked for what mu was. Next topic, Hooke's law. So these are all just different kinds of forces that can be on our free body diagram. Hooke's law you only use with springs. Only applies to springs. Don't overuse this equation. It says that the spring force on my object by the spring is negative kx. Fs is the spring force, and that would be because it's a force in newtons. K is the spring constant, so that would have units of Newton per meter. That is a constant, but it has units, unlike mu. Coefficient of friction, no unit. Spring constant, yes unit, Newton per meter. And then x is the displacement in meters. Could be positive or negative, depending on which way the object is displaced. Let's try an example. If you have a spring that extends 10 centimeters when you hang a mass from it, it's a mass of 100 grams is attached to it, and we would like to know, in this case, what is the spring constant? Sometimes you're given the spring constant and you would be, asked to calculate a force. In this case, we want to know what the spring constant is. Identify what variable you are solving for. Spring constant is K. Highly recommend, unless this comes very easily for you, that you make a list of every variable that appears in any equation on your equation sheet. And you know what the name of that variable is. You know what the symbol is, right? K, mu, for instance, any of those. And you know what the unit is, if appropriate. So we draw a picture here. We have the spring in the unstretched position, the spring in the stretched position. Once you put the mass in, of course, it's going to extend downward. We want to know what the spring constant is. So because we want to know, this has to do with forces, so of course we're going to draw a free body diagram. We have the weight. This is going to be a free body diagram of the mass that was attached. So that mass has weight. It is balanced out by the spring force up. We know that those will be equal length vectors because when you attach that mass and it just comes to rest, it's not moving, right? So therefore that is not accelerating. V is a constant value of 0 if the mass is just hanging there. So once we have a free body diagram, rewrite sum of the forces equals ma. Every time you have a free body diagram, you write sum of the forces equals ma. Instead of writing sigma f, instead of writing sum of the forces, I'm going to go ahead and sum the forces that are on my free body diagram. I'm going to add up all the up vectors. I'm going to subtract off all the down vectors. That's what we mean by summing the forces. Add up all the up vectors, subtract off all the down vectors. We have one up vector, and that is spring force. We subtract off the down vector, which is, there is only one, weight. Fs minus w equals 0. I put 0 because, again, I know that if the mass is just hanging there, it is not accelerating. So I'm making some progress. I now have something that has spring force in it. Spring force equals weight. Instead of writing spring force, I'm going to substitute in the equation for spring force, which is negative kx. Instead of writing w, I'm going to write mg. I'm just trying to work this towards the things that I know. Right? I know the mass, I know the x, the displacement, so I'm just trying to get, because I don't know what the value of the weight is, I'm just going to put in an expression for it. You could go calculate the weight separately and then just put a number in instead of writing mg. That would be fine too. So I have negative kx equals mg, so I'm going to solve that for the variable I'm looking for, which is k. K equals negative mg over x, rearranging with algebra. And now I just have to make sure I put in the correct numbers for everything. There's a negative sign there that was in the original expression, so I have to rewrite it. And then what is the mass? 0.1 kilograms. I have to be in kms units, kilograms, meters, and seconds. So I don't put in 100 grams, I put in 0.1 kilograms. Write down those conversion factors on your note sheet if you need them. And then g is 10 meters per second squared. And then I divide that by the displacement, which is negative 0.1 meters. Negative 0.1 meters, because what is the direction that that spring, end of the spring, moved? Down, so negative. What if you forgot that negative sign? If you tried to just put in 0.1 meters, you would end up with a negative number. Is it reasonable to have a negative value for k? No. Where our rule is k has to be a positive number. So if you're doing something that's giving you a negative value for k, you're making a mistake. So just pause, go back, and look and see. Maybe you just forgot, something like the fact that that displacement would have to be down, and so negative. So we get a number for k. It's 10. The unit is newtons per meter because that numerator was kilogram meter per second squared. That's a newton per meter. That's a reasonable number. It came out positive like I expect. I was going to just work through this falling woman problem where she tragically falls from a hotel window. Luckily, she lands on a ventilator box, which collapses 1 meter while stopping her fall. And we want to know what the force is on the woman by the box, on the woman by the box while she's sinking into it, while she is coming to a stop. So sometimes the tricky thing here is deciding what is the part of the motion that we are concerned with. And the part that we're concerned with is just when she is coming to a stop. So when we don't care when she, jumped out of there or fell or whatever from the hotel window and how she sped up because she was in free fall. That happened, we would assume, but that's not the part that we're worried about, because it says that her speed on reaching the top of the box was estimated to be 16 meters per second, and we know she comes to a stop. That tells me that she ends up at v equals 0. That's the only part that we are concerned with. So we know her mass. We know the displacement of her while she is stopping, right, collapses 1 meter, and we want to know a force. We are asked about a force, and so we know that in our future is a free body diagram. In this problem, though, we also need our picture representation. And the way I know that I'm going to have to do that picture representation and assign all those variables is because I have things like velocities and displacements. That's what tells me that. So I go ahead and do that. I say the moment she hits the top of the box, we're going to call that y0 is 0 meters. We're going to say that's when we start the clock, is 0 seconds. And it told us that her speed was 16 meters per second. That's going to be a negative 16 meters per second in my picture representation because she is traveling, according to my motion diagram, in the downward direction. So that's going to be a negative velocity. Speed doesn't tell me direction. Speed is 16 meters per second. V, velocity, has to tell me direction. So that's negative 16 meters per second. When she comes to a stop, she is now 1 meter lower than she was, so she's at a position of -1 meter. We have no idea how much time it took, so I just say T1 equals question mark, and then V1 is 0 meters per second. So this lets me find a delta y is there's an extra dot there, -1 meter. Delta t, we have no idea, and we don't know acceleration. Now, this is an important part here. We do not know her acceleration. The fact that she was in free fall before she hit the box has nothing to do with her acceleration once she hits the box. She is not in free fall, so acceleration does not equal g. A does not equal g, does not equal -10 meters per second squared here, because as soon as she touches the top of the box, her free body diagram is not just her weight anymore. She is not free of all other objects. So A does not equal G. We don't know A. So we know that there are forces involved, so we're going to draw a free body diagram, of course. I'm going to draw that free body diagram. I start with the weight. And then what do I know about the normal force? Normal force is going to be pushing up on the woman by the box, but I draw that vector longer because I know that my motion diagram said her acceleration is up. Therefore, the net force is up. Therefore, normal force has to be greater than her weight. That's the only way I could draw a free body diagram that would be consistent with my motion diagram. Net force and acceleration have to match. If my acceleration vector is up, which it is based on her downward velocity vectors have to get shorter and shorter, so that's an acceleration up. That's the only way I can draw my free body diagram and make that match. Once I draw a free body diagram, I write sum of the forces equals ma every time. It's just automatic. After I draw a free body diagram, I write that. So I have normal force minus weight equals ma. Now I can't say 0 there. I can't say that normal force minus weight equals 0 because it doesn't. She does have an acceleration. Her velocity is changing while she is in contact with the box there. So you cannot say normal force is equal to weight or normal force n minus w equals 0. It doesn't. She has an acceleration. We know that from our motion diagram. So there are several ways to solve it. Once you get it to n minus w equals ma, that is the key step. You have to be able to do that step in order to do anything else. So I'm going to choose to do this where instead of writing w, I'm going to write mg. And then I can solve for the normal force. That would be the force on the woman by the box. That's the one I'm solving for. What is the force on the woman by the box? And so n equals ma plus mg. Again, if you want to put numbers in, that's fine. And so then I'm all happily putting in my numbers here, and I say a normal force equals ma plus mg. Do I know the mass? Sure, 80 kilograms. Do I know her acceleration? No, because in my picture representation, I have a equals question mark. So I just leave it blank for now. And then do I know, so if there's anything else I'm missing, do I know her mass? Yes, I put in 80 kilograms. Do I know g? Yes, 10 meters per second squared. Again, that 10 meters per second squared doesn't mean she was in free fall. That's just for calculating weight. So I don't know what her acceleration is, and so I'm kind of stuck here for finding the force, except I have all of those velocities and displacements. So that tells me look for a motion equation that has the things that I need in it. So I need a motion equation that doesn't have time, because I don't know time. So that gives me only one choice. Vf squared equals vi squared plus 2a delta x. I'm just going to write delta y since I have vertical motion. And then her final velocity is 0. I've already written all these numbers down. I'm just going to go ahead and put them in. 0 squared equals, her initial velocity was -16, which then gets squared. So it's -16 in parentheses. It gets squared. Plus 2 times a times what was her displacement? -1 meter. She moved 1 meter in the downward direction. So that's a -1. 0 squared is 0, -16 quantity squared is 256, negative times a negative is a positive, so 256 minus 2a, simplifying that last term, so bring the 256 to the other side by subtracting, so -256 equals -2a. Oh, look how great that is. A negative divided by a negative when I solve for a gives me a positive number for acceleration, which I'm happy about because my acceleration vector points up. if I forgot a negative in there, right, if I had delta y as just being 1 meter, then I would have gotten mathematically, the math would have given me a negative acceleration, and I would know I did something wrong, which makes me pause, go back, and see where I made the mistake. So I got a positive acceleration, so I'm good with that. So that means that I can put that number in for her acceleration. Now that's her acceleration just while she is coming to a stop. So in order for that to be true, for her to accelerate with that acceleration, the normal force on her would have to be 11,040 newtons. That normal force is greater than her weight. This is an 80 kilogram woman, so her weight is 800 newtons. The normal force that I solved for is greater than her weight. Therefore, that matches with my free body diagram. You have to do those checks and make sure that everything is all telling the same story. So if you did not independently, without any helps, do this problem before, I would go back and rework this problem from scratch. This was just one of your homework problems. That's always your sign of success, when you are able to rework the problem independently, especially if you needed help the first time. All right, that brings us to an end. Thank you for your attention, and good luck on your exam.